Okay, so recall the general event-oriented simulation process is we define the system state, in other words, how we will represent the components of the system state that are important to our simulation, identify the events that change the system state. So recall an event is an instantaneous occurrence that changes the system state somehow. Then identify the processing logic for each event. So we will have defined the system state, the events, and then what happens when an event occurs. Once we have that, then the process basically follows uh, like so. You place an initial event on the event calendar so that we can prime the simulation or get things going. We set the simulation time to 0. While we still have future events, in other words, we look forward on the future event list or in the event calendar, and while we still have events, we get the next one, next being chronologically, so the one that's going to happen the soonest relative to the current simulation time. We jump to that simulation time. We then process the event using the processing logic that we've defined for that event, and we just continue in this loop until we run out of events. And during the whole process, we are tracking statistics to monitor the performance of the system. So let's look at another example. The example that we're going to look at here is a little bit more comprehensive than our previous examples. What we have is a simple restaurant where we have arriving customers. Oops, I don't want that. Let me go back, get my pen. Yes, we have arriving customers, and when a customer walks in the door, the customer sees 3 lines, and the customer chooses the shortest line. When they get in the line, then they wait, and when the corresponding clerk is available, or cashier, I'm sorry, we have 3 cashiers. When the cashier is available, the cashier takes the customer's order. Then the cashier puts the order into the kitchen. And so the kitchen has a queue of orders waiting to be cooked. When the order is finished, it goes to a delivery person, and there's a delivery person queue, and the food is delivered to the customer. So the customer arrives, and once the customer places the order, the customer goes and sits down. It's the order that we're interested in, though. The order goes from the cashier to the kitchen, from the kitchen to the delivery person, and then we're finished. The cashiers each have capacity 1, so they can be serving 1 customer at a time. The kitchen has capacity 6, so the kitchen can be cooking 6 meals simultaneously. And for this model, the delivery person, we only have 1 delivery person to take the food. So the first step in our event-oriented simulation process is to define the system state. Well, I did that again. Let me go back. We want to define the system state. And in our system, there are really 2 types of things that we're interested in. We're interested in the queues, so we have a queue in front of each one of the cashiers, a queue in front of the kitchen, and a queue in front of the delivery person. And we're also interested in the busy idle state of each one of the servers. And so let's tackle the queues first, and let's say that we're going to have our system state defined, or the queue component of our system state defined as follows. I'm going to have in queue C1, in queue C2, in queue C3, in queue K, and in queue D. And so this corresponds to the number of entities in each one of the respective queues. And so our state representation, or our state components, can take on any integer value, including 0. So you can have 0 people in the queue, 1, 2, 3, and so on. Now, in terms of the corresponding servers, we are going to designate that with a B. And so we'll have BC1, BC2, start that one over, BC3, BK, and BD. And the values BC1, BC2, BC3, and BD can take on the value of 0 or 1, whereas the kitchen, since it can cook 6 meals simultaneously, can be 0, 1, 2, up to 6. So in our previous example, we had the busy idle being Boolean, either 0 or 1. and that works when you have a single server, a single capacity server. In this case, the kitchen can either be serving or cooking 0 meals, 1 meal, 2, 3, 4, 5, or 6 meals. So before we continue with the next step, which is defining the events, let's investigate the system state just a little bit more. And what I want to do is specify the system state as a vector. So let's say S is equal to NQC1, NQC2, NQC3, NQK, NQB. So the first 5 elements of our vector are the Q states. Then we have the busy states. So BC1, BC2, BC3, BK, BD. So we have a 10 element vector where each element corresponds to one component of the system state. And so let's say at some point in time we're in the following state: 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And so what this means is that there's nobody in the system. And so this is what's typically referred to as the empty and idle state. Empty and idle. No one's there and no one's busy. And so let's think about if we're in this state and a customer arrives. So if a customer arrives, what's going to happen? Well, that customer is going to look at the queues and see there's nobody in line. So the customer is going to pick one. Let's just say it picks C1, so it gets in line 1, and then immediately begins service. So we would then transition to state 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, indicating that now the cashier 1 is busy and no one else is in the system. Similarly, let's say at some point in the future we're in state 4, 2, 3, 4, 2, and then all of these guys have to be busy, so that's 1, 1, 1, 6, 1. And so in this state, all of the servers are busy, 1, 1, 1, 6, so the kitchen has capacity 6. It's currently cooking 6 meals, and then 1 for the delivery person. In addition, there are 4 people waiting for cashier 1. There are 2 people waiting for cashier 2, 3 people waiting for cashier 3, 4 meals waiting to be cooked, and 2 dinners waiting to go out. And let's say the next thing that happens is the kitchen finishes one of its 6 meals. Okay, so the kitchen finishes cooking. So what happens? Well, this meal goes to the delivery person. Since the delivery person is busy, we will increase this value to 3. Then one of the meals waiting in queue for the kitchen will immediately start being cooked. So this one changes to 3, and nothing else changes. So we have 4, 2, 3, 1, 1, 1, 6, 1. Similarly, let's say someone else arrives. So now we're in this state and another customer arrives. The customer is going to look at these queues and choose line 2. And so we transition to state 4, 3, 3, 3, 3, 1, 1, 1, 6, 1. And so you can see our state representation captures all of the information that we think we need, at least that we think we need now, to encode all of the logic, all of the events, and the associated logic. So we're now satisfied with the system state. The next step is to identify, keep doing that, let me go back, get my pen, identify the system events. And so we're going to do it this way, events. The first event that we're going to have is when a customer arrives, and I'm just going to call that ARR. ARR stands for arrival. Then what I'm going to do is I'm going to define events for customers arriving at each one of the individual cashiers. We'll talk about this later. We don't really have to have these events, but I'm going to define them anyway. So I'm going to define ARRC1, ARRC2, and ARRC3. So a customer arrives and then at the door, then the customer is going to go through some selection process and then eventually will arrive at one of the cashiers. Then we're going to have a completion on the cashier. We're going to call this completion C1. we'll have a completion C2, a completion C3. Now, when one of the cashiers when the customer leaves the cashier, they immediately go to the kitchen. I'm not going to code an arrival to the kitchen, and again, we'll talk about that in a little bit. I'm just going to have the corresponding completion event. So I'm going to have a completion K. Similarly, I'm going to have a completion D for delivery. And so we have the events arriving to the system, arriving to one of the cashiers, completing on one of the cashiers, completing at the kitchen, and finally completing at the delivery person. Okay, so let's look at our first event. And our first event is arrival. And before we write the pseudocode, let's think about what happens. When a customer arrives, that customer is going to look at the 3 queues, pick the shortest of the 3, and then go to that line. And let's just say that if all of the queues are equal length, we'll go to C1. Okay, so that's the logic of how things are going to work. And so clearly what we need to do is look at our NQ state. So we have NQC1, NQC2, and NQC3, and so from those we can make that decision of which queue to go to. Then once we select one, we will generate or schedule the corresponding arrival event that will occur at the exact same time the customer arrives. Okay, so let's look at that. Let's see if I can move forward. I want to move forward, and we're going to call this ARR. And the first thing we're going to do in our arrival event is we're going to set, let's say, fin, which is just a variable, is equal to the minimum of NQC1, NQC2, NQC3. And so fin is just a number that's going to be the minimum queue length. So if all of these are 0, fin is going to be 0. If this is 1, 1, 2, then it's going to be 1, and so on. So it's just the minimum value of the queue length. Once we know what fin is, we're going to say if NQC1 equals fin, then we're going to schedule a event arrive at C1. So we're going to schedule ARRC1 at T now. So T now we'll just assume is the current simulation time. Otherwise, else if NQC2 is equal to fin, that means the second cashier has the shortest line. We're going to schedule ARRC2 at T now. Else schedule ARRC3 at T now. So in this case, we have picked the minimum queue length, and based on that minimum queue length, we've scheduled the next arrival, and we've scheduled it to occur at the current simulation time. The last thing we'll do here is we'll generate our next arrival. So schedule ARR at T now plus sample, where sample is pulling the next inner arrival time, whether it's pulling it from a table if you have static information or generating it using a random distribution. And so that is the logic for our arrival event, and you can see that we have encoded picking the minimum length line and defaulting to C1 if they're all equal, C2 if C2 and C3 are equal. Of course, we could change that logic if we wanted, but let's just go with this for. So next, let's look at these arrival events to the individual cashiers. So we have arrival C1, arrival C2, and arrival C3. And what I'm going to do is define all of those together and call it ARRCX, where X can take on the value of 1, 2, or 3. Because as we're going to see, the logic is identical for all of these. The only difference is going to be whether we're talking about C1, C2, or C3. So let's think about what happens logically. Once the person walks in and they choose one of the lines, then they're going to look at the busy idle state of the server. If the server is busy, they're going to get in the queue. Otherwise, they're going to immediately begin service. And so we code that, or the logic, as follows. We're going to say if NB of CX is equal to 1, then NQ CX equals NQ CX plus 1. And so they get in line. And so in this case, X could be 1, 2, or 3. And so if the corresponding server's busy, they get in the line. Otherwise, we set the server to busy. So NBCX equals 1. Or the more general notation, we can say NBCX equals NBCX plus 1, which for a single server, single capacity server, it's always going to be 1. But the more general notation is to just increment the value. So we increment the value for the busy, and then we schedule the completion event. Schedule COMPLCX at tnow plus sample, where again we are sampling the service time of the cashier. And so that's it. And so that's the logic, whether an entity arrives at C1, C2, or C3. Now, I mentioned before that we didn't actually have to have these arrival CX events, and so let's talk about that just a little bit. If we go back to our arrival event, we can see that we scheduled arrival C1, C2, C3 at the current simulation time. So we only scheduled those at the current time. There's no other way that we can schedule this arrival CX event. And so because of that, what that tells me, went the wrong way. What that tells me is I don't actually need to have these events defined. Instead, what I could have done was embed the logic right here. So for example, if Q1 was the shortest, instead of scheduling the event to occur at T now, when I schedule this event, I know exactly what's going to happen. This logic, right? When I schedule that event to occur at the current time, this logic will get executed. So I could just as easily have taken all of this logic and put it right here inside this if statement, and I wouldn't need to have I would not need to have these individual arrival events. I would code all the logic inside this single arrival event. So that's just a choice I made when I developed this code or developed the logic, because I thought it made the logic cleaner if I separated those events. But in this case, it is certainly not necessary. Oops, one minor thing that I just noticed in reviewing my video, I used the state NB to represent the number busy, when in fact, when I define my system state, I just used B. So I just used busy C1, busy C2, rather than a number busy C1 and number busy C2. So just go in here and just get rid of this. I can't get rid of that. Let's try that one more time. Let's get rid of that in here, and let's get rid of this in here, and let's get rid of this in here. So now what I meant to do was just have BCX and BCX here rather than NBCX. Sorry about that. I hope that wasn't too confusing. Okay, so now we've completely defined the arrival CX events, and so let's go back. We have done, let's see here. Let's change colors. Let's get a blue. We've done this one. We've done these three in batch. And so let's move on to the completion. And so let's think about what happens here with our completion at the cashier. So when the cashier finishes work, the cashier is going to pass the order to the kitchen. And so if the kitchen has remaining capacity, meaning it's not cooking at least 6 meals, then that meal is immediately started cooking. Otherwise, that customer's order gets placed in the kitchen queue. Okay, so let's look at how we do that. And so as before, I'm going to use the generic definition, COMPLX, which will correspond to all three of our events, completion 1, completion 2, and completion 3. So the first thing we're going to do is say if BK is equal 6, then NQ k equals NQ k plus 1. In other words, we get in the, or the order gets in the kitchen line. Otherwise, meaning bk is less than 6, then we increment bk. bk equals bk plus 1. And here's where we need to do the increment because we have more than single capacity server. And we schedule the corresponding completion event. Schedule COMPLK, completion on K, at T now, current time, plus sample, where in this case sample corresponds to sampling the cooking time. Now, the next thing we need to do, now that we've finished processing the cashier's order going to the kitchen, is we need to check and see, are there other customers waiting in the cashier's line? So if NQCX is greater than 0, meaning there are customers waiting at X at the current cashier, we're going to decrement, pick the first one, NQCX equals NQCX minus, oops, that's the minus sign, sorry about that, minus 1, and schedule the completion, SCHEDULE, schedule completion CX at T now plus sample. Keeping in mind that this sample and this sample are different. I'm just sampling observations. In this case, I'm sampling the cooking time distribution, and in this case, I'm sampling the service time distribution at the cashier. Otherwise, here, the BCX equals BCX minus 1. In this case, the cashier becomes idle. So again, what happens from a logic standpoint when we finish, one of the cashiers finishes, checks the busy state of the kitchen. Is the kitchen at capacity? If so, the order gets in the queue. So we increment the queue for the kitchen. Otherwise, we increment the number busy of the kitchen and schedule the corresponding completion event to happen in the future. Then we look back in the line at the cashier, the corresponding cashier, and if that in queue is greater than 0, meaning there are customers in the queue, we grab the first one by decrementing the queue length, and we schedule the corresponding completion event. Otherwise, meaning that there are no entities in the queue or no customers in the queue, we decrement the busy state of the corresponding cashier. And so you can see how in this case again we've used the X value to correspond to the completion event right here, the completion at CX, the queue right here at CX, and the busy state of CX. And so that's the entire logic that we see for completion at one of the 3 servers. At this point, we have the event logic defined for now the completion on the cashier events. So we have the arrival event, the 3 arrival at cashier events, and the 3 completion. The only 2 remaining events that we need to define the logic for are the completion of the kitchen and the completion of the delivery person, which at this point I'm going to leave for you to do on your own. So let's think about what we have once we have these defined. We then will just follow the execution logic that we see in this process, where in this case an initial event would be an arrival of a customer, and when that arrival occurs it will create future events. So the process event logic for the initial arrival will cause a future arrival to occur, and it will cause a completion at the cashier. The completion at that cashier will then cause a completion at the kitchen. The completion at the kitchen will cause a completion of delivery. And so you can see how the execution of the process logic continues to place events on the future event list. So you follow this same general process again to create the event-oriented model regardless of the simplicity or complexity of the system being modeled. So in the previous example, we looked at a tandem queuing server or tandem queuing system. In this case, we looked at a little bit more complex of a system. But even if we have an extraordinarily complex system, like a complete manufacturing system, a hospital, a worldwide supply chain, or something like that, we follow this same basic process. The thing that will differentiate those models will be the system state representation, the specific events, and then the processing logic that you have for each event. Once we've defined those things, then the actual simulation execution is the same regardless of what type of model you're doing.